Hello, I am Shubham Rai. I will be giving the talk on our paper DiSCERN, Distilling Standard Cells for Emerging Reconfigurable Nanotechnologies. In this paper, we will look at how we can design standard cells for the class of emerging nanotechnologies which shows reconfigurability at transistor levels. So, first of all, what is reconfigurability transistor level and why we need it? So if you look at this curve from 1970 till 2020, so 1970 determines from where the first integrated circuits were started getting popular, and we have seen that from the last 30-35 years, CMOS scaling has been the backbone for the technological advancement we have achieved in electronics. And and I'm not saying that that scaling has stopped. Its scaling is still there, and we can see that the present iPhones have like are based on 7 nanometer technology. But the idea is that as we go closer to nanometer scale, the amount of reliability issues are increasing exponentially, and the cost to performance ratio which CMOS scaling was giving, like let's say 20 years back, is not the same. Now you need to have, for a small increase in the performance, you need to spend more amount of money, right? And we look at this reconfigurable transistor level because we want to achieve something called as functional flexibility, where you can have more functionality per unit chip area or more computation per unit chip area. And there's a class of emerging technologies which actually demonstrate a transistor level reconfigurability. How so? So, in traditionally speaking, the complementary metal oxide semiconductor comes in two forms, basically the NMOS and the PMOS, and they are denoted by the charge carriers which flow through this channel, right? Now, if you look at if we look at the emerging reconfigurability FETs, they are represented in this form, where you have two gate terminals instead of one, where one of the gate terminals is called a program gate. Now, this decides whether this particular device behave as a PMOS or an NMOS, and the control gate is the normal gate which occurs in a normal NMOS or a PMOS, which decides the logic of the transistor. Now, if we take a representative silicon nanowire based RFET, so which is a one-dimensional device, so which is shown by this tube kind of structure. Now, this is the channel, and these are the control gates. These are the gates basically. Now in this case, we have seen that there are multiple gates on a single channel, and that's the second property which you can build over emerging reconfigurable FETs, that you can have multiple gate terminals on a single channel. And it shows, and from the IV curve we can see that the behavior is almost symmetrical from P2 N type in P2 N type functionality. Now, I'm not saying that the silicon nanowire is the only technology which exhibits such kind of reconfigurability, but there are multiple technologies like germanium nanowires, carbon nanotube FETs, graphene PN junctions. Even I recently shown 2D devices like molybdenum ditelluride. These all shows reconfigurable FETs, reconfigurability from P to N type. So this work is kind of technology agnostic, and it caters to any kind of reconfigurable nanotechnologies. Moving ahead, so how does it relate to CMOS? So as we said that this is an RFET with two terminals. So in a simple notation, it can be represented in this format, that you have a PMOS and an NMOS connected to a MUX, where the MUX select line is governed by the program gate. And this MUX actually gives the concept of runtime reconfigurability, that you can change the behavior of this transistor at any time. And so basically this reconfigurability is not a compile time thing, and you can change at any time in the logic design. So this basically changes the way EDA look at these technology, and that's basically the work we are trying to solve in this that's basically the thing which we are trying to solve in this presentation. So from this figure, it seems clear that it encapsulates the p-type and n-type functionality, and depending upon the PG, we choose the functionality what we want. The other aspect of RFETs are that it can support, as we said before, that it can support multiple gate terminals on a single channel. So you can have more than one program gate and even more than one control gate. Now the idea of control gate is that this control gate terminals act as an ANDed structure. So it gives an abandoned functionality. Now what does that mean? That you can connect multiple signals on these control gates, and that will give you an ANDed functionality. So this can be correlated in terms of, like, you can have number of CMOS transistors connected in series, right? But unlike CMOS, which has gate to drain and gate to source resistances and capacitances, these devices does not have those, and this allows us to make larger logic gates, which is not so easy or not so cheap in the traditional CMOS technology. So hence our paradigm changes now. So we can't work with our traditional CMOS based logic gates. So in the RFETs also work in the same notion of the pull up and the pull down network, and in CMOS, if you have to give the correct set of inputs so that one of these networks are on, so that your output is at logic high or logic low. Similarly, the RFETs also work in the same way, but here the configuration input is there, which is basically the input is going to the program gate, and it defines whether the pull up network or the pull down network is switched on at a particular time. And when you change the configuration input, this whole network changes simultaneously, and hence we can have more than one functionality, as we'll see in this logic gates. So you can have a minority where which can behave as an AND and NOR depending upon the value of p equals to 0 or p equals to 1, and similarly you can have XOR 3 which has like a XOR 2 input XOR or 2 input XNOR depending upon the functionality of p, depending upon the input p. You can also implement static logic gates as well, as you can see in the 2 marks. So the benefit comes in these special logic gates, which can encapsulate more than one functionality, and as compared to CMOS, these are very cheap in RFETs. So the next we took is that how we can find standard cells which are suitable for RFETs. Like we had this minority and XOR 3s. What others? And we looked at these questions, that why some gates are implemented efficiently using RFETs, and is an underlying Boolean property which needs to be satisfied? And the answer is yes. The answer is that self-dual functions are implemented cheaply in RFETs. So if you look at a minority logic truth table, you have 3 inputs, and the minority, this is the final output. And if you look at this particular red line, so depending upon this, if we flip the inputs, the output also flips, right? So C can be the configuration input, as we have seen in the previous curve, that C can be the configuration input, which when flipped, changes the pull up and the pull down network to give this minority as the functionality, right? So we came to this conclusion that that if we have self-dual functions where based on one of the inputs, you can change the functionality from minority from a NAND to a NOR, right? And all those Boolean functions which show self-duality can be implemented cheaply in reconfigurable FETs. So the next step was to look at benchmarks to see how many occurrences are such which can be exploited for making such standard cells, right? And on EPFL benchmarks, we found that depending upon the number of input cuts we want to make, we get a different profile of benchmarks based on the self-dual functionality. So you have adder, which can show, like for 3 input cut, 50% of the logic gates which were self-dual. In case of square, if you consider for 6 input cut, you will get around 40% of the self-dual functionality, and this is this all depends upon the benchmark and the profile which you want to do, right? So if we have such logic gates which are self-dual in nature in the generic library, you are bound to achieve better mapping as compared to the traditional CMOS based generic library, which does not have specific self-dual functionalities, right? So if we can, so we did so we included those logic gates from which we got from these standard cells from this experiment into the generic library, and we found that we get good amount of area and delay improvements as compared to the CMOS technology library. So here we have two versions, the hyperbolic B and hyperbolic C. So hyperbolic C is the previous work which we did, and hyperbolic B is the current work. And we can see that from the previous work where we just listed the standard cells from previous other works, based on this self-duality based standard cells excavation, we get improvements in almost all the logic gates, right? So we get more in square C, multiplier C, and even log. We get good improvements as compared to the previous works. So we can see that if we choose proper standard cells which are self-dual, which boast of self-dual functionality, and if we include those into our generic library, we are bound to get better area improvements and better delay improvement as well for RFET based circuits, and that was the main idea behind this work. Thank you.